Look closely at physics, and something strange appears. No matter the field, motion, electricity, heat, fluids, waves, quantum mechanics, even space-time itself, the laws of physics almost always look the same. They are not simple equations like position equals something, energy equals a number. Instead, they say things like how position changes over time, how energy flows from one place to another, how fields evolve moment by moment. Physics, at its core, is not written in numbers, it is written in change, and the mathematical language of change is differential equations. This raises a deep question. Why does nature care about change more than values? Why is the universe described by derivatives instead of simple formulas? This is not just a math question. It is a question about how reality itself behaves. Imagine trying to describe motion without change. Suppose I tell you, this car is at 60 kilometers per hour. That single number tells you almost nothing. Is the car accelerating? Is it slowing down? Is it about to stop? Is it turning? Now, instead, imagine physics saying the car's velocity is changing at this rate. Suddenly, the future becomes predictable. This is the key insight. Static quantities describe snapshots. Differential equations describe stories. Nature does not exist as frozen pictures. It unfolds continuously, moment by moment. Early scientists realized this quickly. Galileo Galilei, 1600s. Galileo discovered that falling objects don't move randomly. Their velocity changes smoothly with time. He did not write equations of position, he studied rates of change. This was revolutionary. Nature behaved as if it followed local rules. Given how things are right now, this is how they change next. That idea would quietly become the foundation of all physics. Everything changed with Isaac Newton. Newton did something radical. He did not ask, where will the planet be? He asked, how does its motion change at each instant? This led to Newton's second law. Force equals rate of change of momentum. Not position, not velocity, but change of motion. In modern language, this is a differential equation. Newton didn't just use differential equations, he invented calculus because physics demanded it. Why? Because gravity does not act all at once. It acts continuously, pulling an object at every moment. Each instant slightly alters motion. Those tiny changes accumulate into orbits, trajectories, and tides. This revealed something profound. Nature updates itself locally, step by step. The universe behaves like it is solving differential equations in real time. Reference: Newton, Philosophiae Naturaliae Principia Mathematica, 1867. Leibniz independently developed calculus for similar reasons. This wasn't a mathematical coincidence, it was a structural feature of reality. One of the deepest reasons physics uses differential equations is this: the universe operates locally, not globally. Nature does not look ahead to calculate outcomes, it does not know the final answer. Instead, at every point in space and time, reality asks only one question. Given what exists right here, right now, how should it change next? This is exactly what differential equations describe. They don't say, here is the final state. They say, here is how things evolve infinitesimally. This principle is called locality.
Why locality matters. Forces act at specific locations. Fields have values at each point in space. Energy flows through nearby regions. Causes precede effects locally. A differential equation connects the value of something at a point to its rate of change at that same point. This structure mirrors how nature actually behaves. If physics were written in algebraic equations alone, the universe would behave as if it knew the future. But it doesn't. It only responds moment by moment. Before the 19th century, forces were mysterious. Gravity seemed to act instantly across space. Electric charges pulled on each other without touching. This disturbed many scientists, including Newton himself. That one body may act upon another at a distance is to me so great an absurdity. Isaac Newton. The solution came with James Clerk Maxwell. Maxwell introduced a radical idea. Forces don't act directly between objects, they act through fields. Electric and magnetic fields exist at every point in space, and these fields change continuously. Maxwell's equations describe how electric fields change, how magnetic fields change, how changes in one create changes in the other. Every one of Maxwell's equations is a differential equation. Why? Because fields don't jump. They evolve smoothly from point to point. The stunning result. When Maxwell combined his equations, something extraordinary emerged. Light is a self-propagating wave of changing fields. No light particles were needed, just differential equations governing continuous change. This was one of the greatest triumphs of physics. References: J.C. Maxwell, A Dynamical Theory of the Electromagnetic Field, 1865. Hertz later confirmed electromagnetic waves experimentally, 1887. Once again, reality spoke in derivatives. Now we move from forces to irreversibility. Why does heat flow from hot to cold? Why does smoke spread in air? Why don't broken cups reassemble? The answer lies in diffusion equations. Joseph Fourier, 1820s. Fourier studied how heat flows through solids. He discovered a simple but profound law. Heat flows in the direction of the temperature gradient. This leads to the heat equation, a differential equation. What makes this equation special is that it introduces an arrow of time. Unlike Newton's laws, which are reversible, the heat equation only moves forward. Why? Because it describes how local imbalances smooth out over time. High concentration spreads out. High temperature cools down. Sharp differences fade. This revealed something deep. The universe prefers gradual change over abrupt jumps. Diffusion equations appear everywhere: heat transfer, particle spreading, probability in quantum mechanics, even neural activity in the brain. Nature doesn't teleport information, it lets it flow, and flow requires differential equations. References: J. Fourier, Theory Analytical of the Light, 1822, Fick's Laws of Diffusion, 1855. Why does heat flow from hot to cold? Why does smoke spread in air? Why don't broken cups reassemble? The answer lies in diffusion equations. Joseph Fourier, 1820s. Fourier studied how heat flows through solids. He discovered a simple but profound law. Heat flows in the direction of the temperature gradient. This leads to the heat equation, a differential equation. What makes this equation special is that it introduces an arrow of time. Unlike Newton's laws, which are reversible, the heat equation only moves forward. Why? Because it describes how local imbalances smooth out over time. High concentration spreads out. High temperature cools down. Sharp differences fade. This revealed something deep. The universe prefers gradual change over abrupt jumps. Diffusion equations appear everywhere: heat transfer, particle spreading, probability in quantum mechanics, even neural activity in the brain. Nature doesn't teleport information, it lets it flow, and flow requires differential equations. References: J. Fourier, Theory Analytical of the Light, 1822, Fick's Laws of Diffusion, 1855. Pause review request. We've now gone well beyond basics, covering locality as a principle of reality, fields replacing action at a distance, time's arrow emerging from differential laws. Before I proceed to sections 7 through 9, where we enter quantum mechanics, Schrödinger's equation, and why probability itself evolves via differential equations, please tell me, is the depth still comfortable? Should I slow down or go even deeper? More philosophy or more physical intuition? Once you approve, I'll continue. Go deeper. Perfect. Now we enter the deep, deeper, advanced territory. This is where the topic becomes truly profound. At the start of the 20th century, physics faced a crisis. Classical equations worked beautifully for planets, machines, and waves, but completely failed at the atomic scale. Electrons did not behave like particles. Light did not behave like waves. Reality itself seemed confused. Then came Erwin Schrödinger. Instead of asking, "Where is the electron?" Schrödinger asks something far stranger. How does the state of the system change over time? The result was the Schrödinger equation, a differential equation governing the time evolution of the wave function. Importantly, the wave function is not an observable object. It encodes probability, and probability itself evolves continuously. This was shocking. Even uncertainty obeys a differential equation. Why this matters deeply? Quantum mechanics does not describe things. It describes how possibilities change. At every instant, the wave function updates locally, following a precise differential law until a measurement forces a discontinuous jump. Between measurements, reality flows. This suggests something extraordinary. Even at the deepest level we know, the universe evolves, it does not jump. References: E. Schrödinger, Quantization as an Eigenvalue Problem, 1926. Dirac, The Principles of Quantum Mechanics, 1930.
If Newton made gravity a force, Einstein made it evolution of geometry itself. In general relativity, gravity is not a pull. It is the change of space-time curvature in response to matter and energy. Einstein's field equations are among the most complex in physics, yet structurally they're still differential equations. They relate how space-time curves to how energy and momentum are distributed, locally, point by point. Why differential equations again? Because space-time is not a rigid stage, it is a dynamic entity. As matter moves, space-time changes. As space-time changes, matter moves. This mutual interaction can only be expressed through continuous local variation. Experimental confirmation. Mercury's orbit precession. Gravitational lensing. Gravitational waves detected by LIGO 2015. Gravitational waves themselves are ripples of changing geometry. They propagate as solutions to differential equations. Even space and time are not static. They evolve. References: A. Einstein, The Field Equations of Gravitation, 1915. LIGO Scientific Collaboration, 2016. At this point, a pattern becomes impossible to ignore. Across classical mechanics, electromagnetism, thermodynamics, quantum theory, and general relativity, the universe seems built on one principle. The present determines the future through infinitesimal change. Differential equations encode exactly this idea. They assume continuity, local causality, smooth evolution, no foresight of final outcomes. In other words, the universe does not solve problems, it updates itself. Each moment is computed from the previous one. This may explain why laws are simple locally, but outcomes are complex globally, and chaos can emerge from deterministic rules. Differential equations are not just convenient tools, they may be the native language of causality itself. Up to now, many examples sounded smooth and predictable, but most real physical systems are not. They are non-linear. A non-linear differential equation is one where outputs are not proportional to inputs. Small changes can grow dramatically. Solutions cannot be written in closed form. This is not a flaw, it is a feature of nature. Edward Lorenz and Chaos, 1960s. Lorenz studied a simplified model of atmospheric convection using three coupled differential equations. What he found shocked physics. Two simulations with almost identical initial conditions diverged rapidly, producing completely different weather patterns. This was not randomness, the equations were deterministic. This is now called chaos theory. The lesson:
Even when nature obeys precise differential equations, long-term prediction may be impossible. Yet the law itself remains differential. Why physics still uses them? Fluid dynamics, Navier-Stokes equations, plasma physics, climate models, turbulence, astrophysical disks. All are governed by nonlinear differential equations. Nature is not linear, but it is still locally evolving.
References: E. Lorenz, Deterministic Non-Periodic Flow, 1963. Ruel and Takens, Turbulence Theory, 1971. At this stage, a serious scientific question arises. Is the universe actually continuous? Differential equations assume smooth space, smooth time, and infinitely small changes. But modern physics challenges this assumption. Atomic and quantum limits. Matter is discrete, atoms, particles. Energy is quantized, measurements are finite. Yet differential equations still work astonishingly well. Why? Because most physical laws describe averaged behavior, pressure from many molecules, fields from countless charges, probability from many quantum events. This leads to effective continuum theories. Example, fluid mechanics. Navier-Stokes equations assume continuous fluids, but fluids are made of molecules. Still, predictions match experiments across vast scales. Turbulence statistics remain accurate, engineering relies on them daily. This tells us something critical. Differential equations describe emergent behavior, not necessarily microscopic reality. They are valid where large numbers smooth out discreteness. References: Chapman-Enskog theory, kinetic to fluid equations, Landau and Lifshitz, fluid mechanics. Science advances by finding where models break. Differential equations are no exception. Known breakdowns. Quantum measurement. Schrödinger equation is continuous. Measurement introduces discontinuous collapse. Singularities. Black hole centers. Big Bang initial conditions. Curvature becomes infinite. Equations fail. Quantum gravity. Space-time may not be smooth at Planck scale. Differential geometry may no longer apply. Modern research explores alternatives: lattice quantum field theory, discrete space-time models, causal sets, and loop quantum gravity. Yet even these theories recover differential equations at large scales. This suggests differential equations may not be fundamental, but they are inevitable at observable scales. They are the bridge between microscopic rules and macroscopic laws. References: Hawking and Penrose singularity theorems, Ravelli, quantum gravity, Wilson, renormalization group theory. At the most fundamental level of physics, reality is described not by particles alone, but by fields. Electrons, quarks, photons, all are excitations of underlying fields. Each field obeys quantum field equations, which are essentially operator-value differential equations. Example: Klein-Gordon and Dirac equations. Klein-Gordon equation describes scalar fields like Higgs field in spacetime. Box plus m squared phi equals 0, where box is the D'Alembertian operator, a second-order differential operator. Dirac equation describes half-spin particles, electrons, quarks, by I gamma mu partial mu minus m psi equals 0. Both are differential equations in space and time governing probability amplitudes and field evolution. Why QFT still uses differential equations? Even at quantum scales, locality remains fundamental. Causality must be respected. Continuous evolution between interactions is required. Differential equations allow precise predictions of particle interactions as confirmed by experiments. One of the deepest insights of modern physics is that laws change with scale, yet differential equations still govern evolution. Renormalization group, Wilson, 1970s. Fundamental interactions are described by differential equations that evolve coupling constants with energy scale. High-energy physics, small distances, behaves differently from low-energy physics. The beta function is a differential equation describing how a parameter changes with scale. B of g equals mu times dg over d mu. This explains why electromagnetism and weak force unify at high energies, how quantum chromodynamics becomes strongly coupled at low energies, and why phase transitions in condensed matter can be predicted. Differential equations here are not just mechanics, they encode universality across scales. Modern experiments and simulations rely heavily on differential equations. Examples: climate modeling, Navier-Stokes plus thermodynamics plus radiative transfer. Millions of coupled PDEs simulate Earth's atmosphere. Astrophysics, supernova explosions, accretion disks, gravitational wave sources. Differential equations evolve matter and spacetime. Condensed matter physics, Schrödinger equation in lattices, time-dependent DFT, density functional theory, particle physics simulations. Lattice QCD solves QCD differential equations on a discrete spacetime lattice, provides precise predictions of hadron masses. Even when exact solutions are impossible, numerical methods like Runge-Kutta, finite elements, and spectral methods rely on differential equations as the backbone of reality. References: Press et al., Numerical Recipes, 2007, Levesque, Finite Difference Methods for Differential Equations, 2007, Shankar, Principles of Quantum Mechanics, 2012. Even in quantum mechanics, deterministic differential equations can lead to unpredictability when systems are complex. Studies quantum systems whose classical analogues are chaotic. Schrödinger equation governs evolution of probability amplitudes, but interference patterns and eigenvalue spectra show sensitivity to initial conditions. Example: stadium billiard. A particle in a stadium-shaped potential shows classical chaos. Its quantum counterpart exhibits random matrix statistics in energy levels. Differential equations still govern dynamics, but long-term predictions are statistical. Experimental confirmation: microwave resonator experiments reproduce quantum billiard statistics. Cold atom experiments simulate chaotic potentials. Observations match solutions of time-dependent Schrödinger equation. Beyond linear fields, many real systems are nonlinear, creating rich structures. Examples in physics: nonlinear optics, light propagation in nonlinear media. Nonlinear Schrödinger equation predicts solitons and optical turbulence. Plasma physics, magnetohydrodynamics (MHD) uses coupled nonlinear PDEs, predicts solar flares, tokamak instabilities, and astrophysical jets. Bose-Einstein condensates. Gross-Piotrowski equation, a nonlinear Schrödinger equation, describes collective quantum behavior of ultra-cold atoms. These equations predict emergent phenomena unseen in linear approximations. Many modern problems cannot be solved analytically, yet differential equations remain the core framework. Cutting-edge applications. Lattice quantum chromodynamics, Lattice QCD, solves QCD differential equations on a discrete grid, predicts hadron masses, cork-gluon plasma properties, requires supercomputers. Simulations of black hole mergers. Einstein's field equations solved numerically, predicted gravitational waveforms before LIGO detected them, requires solving coupled nonlinear PDEs in 3+1 dimensions. Turbulent flows. Navier-Stokes equations describe turbulent fluids. Direct numerical simulation, DNS, matches experiments in aerodynamics. Why this matters scientifically. Differential equations are not optional. They allow quantitative predictions. They form the interface between theory and experiment. Even in extreme or chaotic regimes where analytic solutions fail, numerical solutions of differential equations reproduce reality with astonishing accuracy. At extremely small scales, around 10 to the minus 35 meters, the Planck length, spacetime may no longer be smooth. Einstein's field equations assume continuity of spacetime, but at Planck scale, quantum fluctuations dominate. Differential equations might break down, yet physicists still try to formulate evolution laws. Approaches involving differential equations. Loop quantum gravity, LQG. Space is quantized into spin networks. Dynamics can be approximated with discrete versions of differential equations. Operators evolve nodes and links locally in time-like parameters. Causal dynamical triangulations, CDT. Spacetime emerges from small simplices. Evolution rules mimic discrete differential equations, recovers smooth spacetime at large scales. String field theory. Strings evolved according to field equations in higher dimensions. Differential equations govern vibrational modes and interactions. Even at these extremes, continuity emerges at larger scales, making differential equations effectively universal. References: Rovelli, Quantum Gravity, 2004, Amjorn, Yurkevich, Lal, Emergence of a 4D World from Causal Quantum Gravity, 2005, Kaku, Introduction to Superstrings in M-Theory, 1999. Sometimes differential equations do not describe fundamental objects, but emerge from collective behavior. Examples: superfluidity and BECs. Millions of atoms behave as one quantum object. The Gross-Pitavisky equation describes the condensate's wave function. A differential equation emerges from quantum many-body dynamics. Condensed matter emergent fields, quasiparticles, phonons, magnons obey effective PDEs. Underlying lattice is discrete, but emergent behavior is continuous. Biophysics, neural networks, population dynamics, chemical reactions. Differential equations describe averaged rates of change. Micro-level randomness aggregates into smooth macroscopic law. Differential equations capture universality, even if the microscopic world is granular or quantum. References: Pethick and Smith, Bose-Einstein condensation in dilute gases, 2008, Anderson, More is Different, 1972, Strodgatz, Nonlinear Dynamics and Chaos, 2018.
Einstein's equations are notoriously complex, especially for systems like merging black holes or neutron stars. Numerical relativity uses discretized differential equations to simulate extreme gravitational events. LIGO's detection of gravitational waves, 2015, depended on solutions of coupled nonlinear PDEs. Simulations predicted waveform signatures before experimental confirmation. This is a modern triumph. Differential equations are both theory and computational tool. They bridge abstract mathematics and observable phenomena. Other applications: core collapse supernova simulations, binary neutron star mergers, accretion disk dynamics around black holes. At high energies, quantum fields interact non-linearly. Examples: quantum chromodynamics, QCD, governs strong nuclear force. Nonlinear differential equations describe gluon interactions, explains confinement of quarks inside protons and neutrons. Electroweak unification. SU2 times U1 gauge fields are nonlinear. Differential equations dictate particle interactions in colliders. Higgs field dynamics. The evolution of the Higgs field in the early universe is governed by PDEs, critical for cosmology and particle masses. Even in quantum fields, predictive power relies on differential equations despite extreme nonlinearity. The universe itself evolves according to differential equations. Cosmology is built on dynamical equations of spacetime, matter, and radiation. Friedmann equations, derived from Einstein's field equations assuming homogeneity and isotropy, A over A equals minus 4 pi g over 3 times rho plus 3p plus lambda over 3. A over A equals 8 pi g over 3 times rho minus k over A squared plus lambda over 3, where AT equals scale factor, rho equals energy density, P equals pressure, K equals curvature, and lambda equals cosmological constant. These differential equations predict expansion of the universe, acceleration due to dark energy, Big Bang dynamics, inflationary dynamics. Inflaton field, phi equals phi of t, evolves according to Klein-Gordon equation in expanding spacetime. phi dot dot plus 3 times h phi plus v prime of phi equals 0, where h equals a dot over a is the Hubble parameter, and v of phi is the potential. Explains rapid early expansion and smoothness of the CMB. References: Peebles, Principles of Physical Cosmology, 1993. Little and Lith, Cosmological Inflation and Large-Scale Structure, 2000. Guth, Inflationary Universe, 1981. Differential equations are crucial for predicting how small density fluctuations grow into galaxies and clusters. Linear perturbation theory. Density contrast, delta equals rho minus rho bar over rho bar, evolves according to delta dot dot plus 2 times h delta dot minus 4 pi g times rho bar delta equals 0. Predicts growth of cosmic structures over billions of years. Once density contrasts grow large, full n-body simulations are required. Governed by Newtonian gravity in co-moving coordinates. d squared x vector I over dt squared equals g times the sum of j not equal to I, mj times x vector j minus x vector I over the magnitude of x vector j minus x vector I cubed. Effectively solves millions of coupled differential equations. Matches observed large-scale structures.
Experimental confirmation. Cosmic microwave background anisotropies, galaxy surveys, SDSS, DES, simulated power spectrum match observations with high precision. Differential equations govern not only cosmology, but also stellar, galactic, and planetary dynamics. Hydrostatic equilibrium, dp/dr, equals minus gm of r rho of r over r squared. Energy transport, radiative or convective, dt/dr equals minus 3 kappa rho L of r over 16 pi a cr squared t cube. Coupled with nuclear reaction rates, full differential equation system. Predicts main sequence, supernovae, neutron stars. Planetary systems, n-body differential equations. Small changes in initial positions to chaotic trajectories. Still solvable numerically to predict stability zones. Collisionless Boltzmann equation, partial f over partial t plus v arrow dot nabla x f minus nabla phi dot nabla v f equals 0. Describes stellar motions and dark matter halos. Differential equations allow quantitative astrophysics. Supernova light curves, galactic rotation curves, black hole accretion dynamics. References: Kippenhahn and Weigert, Stellar Structure and Evolution, 1990, Binney and Tremaine, Galactic Dynamics, 2008, Lichtenstein and Lieberman, Regular and Chaotic Dynamics, 1992. Neutron stars represent one of the most extreme laboratories for physics. They compress more mass than the Sun into a sphere 10 to 12 kilometers across. Their structure is governed by relativistic differential equations. 1. Tolman-Oppenheimer-Volkoff equations. These are the general relativistic extension of hydrostatic equilibrium. dp/dr equals minus g times rho plus p over c squared times m plus 4 pi r cubed p over c squared, all over r times r minus 2 gm over c squared. dm/dr equals 4 pi r squared rho. These coupled differential equations determine maximum neutron star mass, radius-mass relation, and collapse into black holes. 2. Equation of state. Pressure P of rho comes from nuclear physics. Different equation of states leads to different solutions of TOV equations. Gravitational wave observations now constrain equation of state experimentally. Observational confirmation. Binary neutron star merger WG1 71081. Tidal deformability extracted via numerical relativity. Matches solutions of relativistic differential equations. Many cosmic objects are dominated not just by gravity, but by magnetic fields and plasma dynamics. Magnetohydrodynamics.
Magnetohydrodynamics combines Navier-Stokes equations, Maxwell's equations, conservation laws. The result is a highly nonlinear system of PDEs. Applications: magnetars, magnetic fields up to 10 to the 15 Gauss, field evolution governed by Hall drift and ohmic diffusion equations, explains starquakes and gamma-ray flares. Accretion disks, matter spiraling into black holes, governed by viscous MHD equations. Magnetorotational instability, MRI, enables angular momentum transport. Astrophysical jets, relativistic MHD equations, explain jets extending thousands of light years. Experimental and observational support. X-ray timing, radio polarization, event horizon telescope observations. References: Balbus and Hawley, MRI and accretion disks, 1991, Friedberg, Ideal Magnetodynamics, 1987, Rizzola and Zanotti, Relativistic Hydrodynamics, 2013. Black holes are not static objects. They evolve, merge, and ring down, all described by Einstein's differential equations. 1. Binary black hole mergers, governed by fully nonlinear Einstein field equations, solved numerically using 3+1 decomposition, predict in-spiral, merger, and ring-down phases. 2. Quasi-normal modes. After merger, black holes emit gravitational waves at specific frequencies. These frequencies are solutions to perturbation differential equations, depend only on mass and spin. Detected waveforms match predictions to high precision. 3. Black hole stability. Perturbation equations test stability of spacetime. Reggie Wheeler and Tucholsky equations describe wave propagation. At particle colliders like the LHC, predictions depend heavily on differential equations. 1. Quantum scattering, governed by time-dependent and time-independent field equations, cross-sections computed using differential operators. 2. Parton distribution functions, PDFs, describe how quarks and gluons share momentum inside protons. They evolve with energy scale via DG-LAP equations. Partial f of x q squared over partial ln q squared equals sum over j integral of x to 1 dz over z, pij of z, fj of x over z q squared. These are integro differential equations confirmed by experiment. 3. Experimental validation. Precision agreement between QCD predictions and collider data. Higgs production rates predicted using differential evolution equations. References: Altarelli and Parisi, 1977, Collins, Foundations of Perturbative QCD, 2011, CERN, Yellow Reports. Many natural systems are not in equilibrium. Examples: early universe reheating, heavy ion collisions, plasma instabilities, active matter systems. These systems require time-dependent differential equations. Boltzmann and kinetic equations govern evolution of particle distributions, include collision integrals, successfully describe quark-gluon plasma formation. Experimental support: RIC and LHC heavy ion collision data. Hydrodynamic equations reproduce flow patterns.
In the last 2 decades, physics has entered a new experimental era: quantum information and quantum computation. Here again, differential equations are unavoidable. For isolated systems, evolution is governed by the Schrödinger equation. For open systems, interaction with the environment causes decoherence. Evolution follows Lindblad-Master equations. This is a differential equation for information itself. It predicts loss of coherence, error rates in quantum computers, stability of entangled states. Experimental confirmation: superconducting qubits, trapped ions, cold atom systems. Measured decoherence times match solutions of these equations with high precision. So why this matters? Quantum technologies do not work by philosophy. They work only because time-dependent differential equations correctly predict physical behavior. One of the most active areas of theoretical physics today asks a radical question: is spacetime itself emergent? Surprisingly, even these ideas rely heavily on differential equations. First, ADS/CFT correspondence. Gravity in higher dimensional spacetime
equivalent to a quantum field theory without gravity on the boundary. Dynamics on both sides are governed by Einstein field equations, bulk, renormalization group flow equations, boundary. Differential equations link geometry, quantum fields, and thermodynamics. One research shows space-time curvature can be related to entanglement entropy. Entanglement evolves according to quantum evolution equations. Even when spacetime may not be fundamental, its effective behavior still obeys differential laws. In experimental relevance, strongly correlated materials, quark-gluon plasma, non-equilibrium quantum matter. Predictions from these models match experimental results only because the underlying equations evolved continuously in time and scale. At this point, the pattern across all of physics is unmistakable. From falling apples, flowing heat, vibrating atoms, quantum probabilities, collapsing stars, merging black holes, expanding spacetime, the laws that succeed experimentally share a common structure. They are local, time-dependent, predictive, testable. And they are written as differential equations, not because physicists love mathematics, but because experiments demand it. Whenever physics has tried to move beyond them, discreteness, randomness, quantum uncertainty, the result has not been the removal of differential equations, but their re-emergence at larger, observable scales. They are the bridge between microscopic laws and macroscopic reality, theory and experiment, prediction and measurement. And that may be their deepest scientific significance. If you've stayed this far, you've followed physics from simple motion to the edge of modern research, not through equations on a board, but through the ideas that make those equations inevitable. This channel exists for exactly this reason, to slow down, to think carefully, and to understand why nature behaves the way it does. If this journey through physics and change resonated with you, you're already part of the wandering neuron. And if you'd like to keep exploring how science quietly explains reality, you're welcome to stay.